All right, hey AP Chemistry. So I wanted to make a little bit more video notes or notes on Q versus K. So I'm in the Unit 7 Important Information Part 3 notes, Le Chatelier's Principle, and I'm going to jump all the way to page 9. Okay? So on page 9, there is a lot of important information here regarding reaction quotient and Le Chatelier's Principle. So let's look here for a moment. There's this graph that I took directly from your textbook, and I thought it was a beautiful interpretation of comparing Q versus K. So I want to remind you what Q is. Q is a reaction quotient, which is the concentration of products raised to their coefficients over the concentration of reactants raised to their coefficients. I could also use pressures. Pressures of the products, partial pressures of the products raised to a power, partial pressure of the reactants raised to some power. And N is the stoichiometric coefficients. And there's an example here. If I have a reaction of A to B, Q could be concentration of B over concentration of A. And mine's in color. Now, Q, the reaction quotient, is usually a set of initial conditions like concentration and pressures. And what I could do is, if I have initial conditions of all of my reactants and products, if I have an initial amount of all reactants and products, I could solve for my reaction quotient Q and see which direction that reaction will have to go in order to reach equilibrium. And remember, if Q is small, that means my bottom number is bigger and my top number is small. So that means I have too many reactants. So make a note there. If Q is small, I have too many reactants. If Q is large, you're going to see that I have too many products. And so typically, if my Q is small, if it's smaller or less than K, that means I have too many reactants and it's going to go towards products or go to the right. And that's what this graph is saying. When Q is less than K, that means I have too many reactants, like I mentioned there. Too many reactants. And in order for the reaction to progress towards equilibrium, I need to make more products. So when Q is less than K, my reaction is going to shift towards making more products or shift to the right. Right? So there's too many reactants. Got to use those reactants to make products to get to Q. And Q is this one value. This is just an example problem. Now the opposite happens if Q is too large. That means I have too many products. So I got to go back now. I have too many products. I got to shift to the left. Go to my reactant side. So I have too many products. So I'm going to shift to the left and make more reactants. And then when Q is equal to K, nothing's going to happen. We're good. Okay? So I'm going to do an example applying this idea. So I'm going to do sample problem number 8. So this is right in your practice, and I'm probably going to make you do this. But sample problem number 8. Nitrosyl chloride decomposes to nitric oxide and chlorine when heated. Boom. At 600 Kelvin, the equilibrium constant, Kp, is 0.06. So I could write that Kp is equal to 0.060. Cool. In a vessel at 600 Kelvin, there's a mixture of all three gases. The partial pressure of NaCl is 675 torr, the partial pressure of NO is 43 torr, and the partial pressure of chlorine is 23 torr. So I have initial conditions. All of these, right, initially, before equilibrium, right, in a vessel, there's a mixture of all three gases. The partial pressure of NaCl is 6, this is initial. Partial pressure of NO is 43 torr. Chlorine is 23. These are all initial conditions. That's going to be perfect for Q. So it says, what is the value of the reaction quotient Q? Well, Qp is going to be partial pressure of NO squared, partial pressure of Cl2, all over the partial pressure of NaCl, also squared. I'm going to plug in these values that I underlined. These are the initial conditions. This is the reaction happening initially. So I just plug in these values and see which direction eventually will this go to reach my equilibrium constant. So let me plug them in. All right. So P of NO, or NO, is 43, and that's going to be squared. 43 squared. NO is that. PCl2 is 23. Nothing's happening to that. The coefficient is 1. All over 675 squared. So now I'm going to plug these values in. 43 squared times 23 divided by 675 squared. And I get a value of 0.093. Is the mixture at equilibrium? No. This is Q. This is K. It looks like Q is greater than K, not equal to K. The mixture would be at equilibrium if Q was equal to K, but right now my Q is greater than K. In which direction will the system move? Well, since Q is greater than K, I have too many products. That means I have too many products, and I gotta shift that back. And if you look on the page before, if Q is greater than K, reaction is going to go to the left, towards the reactants. If Q is greater than K, that means I have too many products. To get to equilibrium, I have to go back down. I have to make reactants. So, in which direction will the system move? Well, since Q is greater than K, there's too many products. It's going to shift towards reactants. That's it. Okay? Now, after watching this video or checking your work, make sure you could do something like sample problem 9. It is the exact same question, same type of question as sample problem 8. And it was a similar reaction on your problem set, but now I have a different KC and I have concentrations. So solving sample problem number 9 accurately will be a good indication that you understand how to do Q versus K.